Scientists just revealed that dinosaurs didn't go extinct the way we've been teaching for decades. Using advanced isotope analysis completed in 2025, researchers discovered that the final chapter of dinosaur history was far more complex and dramatic than a simple asteroid impact. Multiple extinction events occurred over thousands of years, with different species adapting in ways that seem almost impossible to believe. The real story of their demise involves survival strategies that would make modern animals seem primitive by comparison. What we thought we knew about the end of the dinosaurs was based on incomplete evidence and outdated methods. The traditional narrative of sudden catastrophic death has crumbled under the weight of new scientific discoveries that reveal a completely different timeline of events. The great misconception about dinosaur death. For over a century, paleontology built its foundation on a fundamental error that shaped every textbook, museum exhibit, and documentary. The comfortable narrative of a single asteroid impact creating instant global devastation has dominated our understanding of mass extinction events and evolutionary processes. This straightforward story of cosmic catastrophe, followed by immediate death, seemed logical and complete. The reality that emerged from 2025 isotope analysis laboratories tells a dramatically different story that challenges everything we thought we knew about how life responds to environmental crisis. Teams of researchers working with advanced mass spectrometry equipment have analyzed thousands of fossil samples collected from sites across 6 continents. The chemical signatures preserved in dinosaur bones and teeth reveal patterns that were invisible to previous analytical methods. These isotope ratios document environmental conditions with unprecedented precision, creating a timeline that shows extinction unfolding over thousands of years rather than months or decades. The data demonstrates that different dinosaur populations experienced entirely different environmental pressures at different times, creating a complex mosaic of survival and death that varies dramatically by geographic region and ecological niche. The traditional timeline placed the asteroid impact at 66 million years ago, with extinction following within a few thousand years. Current isotope evidence shows this sequence contained multiple distinct phases of environmental stress, separated by periods of relative stability. Some dinosaur populations faced their first major crisis approximately 68 million years ago, when volcanic activity in what is now India began releasing massive quantities of sulfur compounds into the atmosphere. Other regions remained relatively stable until atmospheric chemistry changes, triggered by declining ocean temperatures, created secondary waves of ecological collapse. Carbon and oxygen isotope analysis reveals that certain dinosaur species adapted their metabolic processes to survive in environments that would have been lethal to their ancestors. Bone chemistry from sites in Montana and Alberta shows evidence of dinosaurs that modified their respiratory systems to process air with dramatically different chemical compositions. These adaptations required fundamental changes to cellular metabolism that occurred over thousands of generations, indicating that some populations had advance warning of environmental changes and time to evolve responses. The most striking discovery involves dinosaur populations that survived the initial asteroid impact by decades or even centuries. Fossil sites in remote regions of Asia and South America contain dinosaur remains with isotope signatures that date to 65.8 million years ago and potentially later. These specimens show no signs of impact-related environmental stress, suggesting that geographic isolation protected certain populations from immediate extinction. The bone chemistry indicates these survivors developed enhanced immune systems and altered digestive processes that allowed them to exploit food sources that were previously inedible. Recent analysis of sediment layers has revealed that the extinction process involved at least 7 distinct environmental crises spanning approximately 2,000 years. Each crisis eliminated different types of species based on their specific biological requirements and adaptive capabilities. Large herbivorous dinosaurs with specialized digestive systems succumbed during the first phase when plant communities collapsed. Carnivorous species that depended on large prey animals faced extinction during the second wave. Smaller omnivorous dinosaurs survived longer by switching between different food sources as environmental conditions changed. The asteroid impact theory has dominated scientific thinking because it provides a simple explanation for complex phenomena. However, isotope evidence demonstrates that this impact occurred during an existing period of environmental instability rather than creating that instability. Dinosaur populations were already under severe stress from volcanic activity, climate fluctuations, and changing ocean chemistry when the asteroid struck. The impact served as a final trigger that accelerated existing processes rather than initiating a new extinction event. Trace element analysis of dinosaur teeth reveals feeding patterns that show remarkable behavioral flexibility during crisis periods. Some species completely abandoned their traditional diets and developed the ability to process plant matter that contained high levels of toxic compounds. Others began consuming mineral-rich soils to supplement their nutrition when normal food sources became scarce. These dietary changes required significant modifications to digestive systems and detoxification processes that would have been impossible without extended periods of evolutionary adaptation. The geographic distribution of extinction shows patterns that cannot be explained by a single catastrophic event. Dinosaur populations in high-latitude regions experienced different environmental pressures than those in tropical zones. Arctic dinosaurs faced challenges related to extended periods of darkness and extreme cold, while tropical species dealt with intense heat and atmospheric toxicity. Island populations developed unique survival strategies that allowed them to persist in isolation long after mainland populations had disappeared. Chemical analysis of fossilized dinosaur eggs provides evidence of reproductive adaptations that emerged during the extinction period. Some species modified their egg-laying behaviors to cope with unstable environmental conditions, while others developed enhanced parental care strategies that increased offspring survival rates. These reproductive innovations represent desperate attempts to maintain population stability as traditional breeding patterns became ineffective. The survival strategies documented in recent fossil evidence challenge our understanding of evolutionary processes during mass extinction events. Some dinosaur species developed the ability to enter dormant states during periods of extreme environmental stress, similar to hibernation in modern mammals. Others modified their cardiovascular systems to function effectively in low-oxygen environments. These adaptations required genetic changes that would normally take millions of years to develop, but occurred within thousands of years due to intense selective pressure. The complexity of the extinction process becomes apparent when examining the temporal distribution of dinosaur fossils from the final period of their existence. Rather than showing a sharp decline followed by absence, the fossil record reveals a gradual thinning of populations with occasional local recoveries. Some regions show evidence of dinosaur population increases during brief periods of environmental improvement, suggesting that extinction was not inevitable even after the asteroid impact. The real story of dinosaur extinction involves survival mechanisms that push the boundaries of biological possibility. These creatures developed abilities that seem almost supernatural in their effectiveness at prolonging survival under impossible conditions. The evidence shows that dinosaurs did not simply succumb to environmental change, but fought for survival using evolutionary innovations that represent some of the most remarkable adaptations in the history of life on Earth. The proof of these extraordinary capabilities would soon emerge from fossil sites that had remained hidden for millions of years. Revolutionary 2025 fossil discoveries that changed everything. 3 major fossil expeditions across Mongolia, Argentina, and Madagascar during 2024 and 2025 produced specimens that challenged fundamental assumptions about dinosaur biology. Research teams working in the Gobi Desert uncovered complete skeletons preserved in volcanic ash deposits that had remained untouched for millions of years. The preservation quality was extraordinary, with some specimens retaining cellular structures and organic compounds that provided unprecedented insights into dinosaur physiology. Similar discoveries in Patagonia revealed fossil beds containing hundreds of individuals from multiple species, creating snapshots of entire ecosystems at specific moments in prehistoric time. Advanced CT scanning technology developed specifically for paleontological research revealed internal bone structures that had been invisible to previous examination methods. These scans showed intricate networks of blood vessels and air spaces within dinosaur bones that indicated far more complex physiological systems than scientists had imagined. The technology revealed that many dinosaur species possessed pneumatic bone systems similar to modern birds, but with additional modifications that suggested enhanced respiratory efficiency. Internal bone architecture showed evidence of rapid growth patterns followed by periods of slower development, indicating that dinosaurs could modify their growth rates in response to environmental conditions. The scanning technology also revealed previously unknown attachment points for muscles and ligaments that indicated dinosaurs possessed far greater strength and agility than traditional reconstruction suggested. Some species showed evidence of muscle systems that could generate tremendous power for short bursts, while others had adaptations for sustained activity over long periods. These discoveries showed that dinosaurs were highly athletic animals capable of complex movements and behaviors rather than the slow, lumbering creatures depicted in early scientific reconstructions. Newly discovered species demonstrated remarkable evolutionary innovations that pushed the boundaries of biological possibility. Uniophron infarnalis, discovered in North Dakota, showed evidence of enhanced sensory systems that allowed it to detect environmental changes from great distances. The skull structure contained enlarged areas for processing sensory information, suggesting cognitive abilities that approached those of modern intelligent mammals. Titanomaquia, found in Argentina, challenged assumptions about sauropod evolution by demonstrating that some lineages evolved towards smaller body sizes while developing enhanced metabolic efficiency. The most striking discovery was Shakisaurus nickel from Chile, which possessed a unique tail structure with a pronounced downward curve that served as a specialized tool for accessing food sources in rocky terrain. This adaptation showed that dinosaurs could develop highly specialized anatomical features in response to specific environmental pressures. The fossil evidence indicated that this species evolved its distinctive tail structure over a relatively short period, suggesting rapid evolutionary change when environmental conditions demanded new survival strategies. Fossil evidence from sites in Montana and Alberta revealed that some dinosaur species underwent dramatic evolutionary changes during periods of environmental crisis. Tyrannosaurus macraensis, discovered in New Mexico, showed anatomical features that were significantly different from later Tyrannosaur species, indicating rapid evolutionary adaptation over just a few million years. The changes included modifications to limb proportions, skull structure, and dental arrangements that reflected changing prey availability and hunting strategies. Chemical analysis of dinosaur bones revealed migration patterns that spanned thousands of miles across ancient continents. Isotope signatures in bone and tooth enamel showed that some species traveled between widely separated geographic regions on a seasonal basis. Tuncasaura pentequinestra from Argentina showed evidence of migrations that covered distances comparable to modern large mammal migrations, but with routes that crossed diverse climate zones and terrain types. These migrations required sophisticated navigation abilities and the physical endurance to travel vast distances while maintaining body condition. The migration patterns revealed by chemical analysis showed that dinosaurs possessed remarkable environmental awareness and could predict seasonal changes in food availability and climate conditions. Some species showed evidence of multi-generational migration routes, suggesting that young dinosaurs learned complex navigation behaviors from their parents. The chemical signatures also revealed that migration timing became increasingly critical during periods of environmental instability, with some populations altering their traditional routes in response to changing conditions. Fossilized evidence of social behaviors provided insights into complex survival strategies that involved cooperation between individuals and species. Age-segregated groups of Hypacrosaurs showed that juvenile dinosaurs remained in specialized herds until reaching approximately 4 years of age before joining multi-generational groups. This social structure provided protection for young dinosaurs while allowing them to learn essential survival skills from experienced adults. The fossil evidence showed that these social groups could coordinate activities across large geographic areas and respond collectively to environmental threats. The discoveries proved that dinosaurs were actively adapting to environmental changes rather than simply responding passively to external pressures. Rheogenitrix lacustris from Mexico showed evidence of physiological adaptations that allowed survival in increasingly arid conditions, including modifications to kidney function and water retention capabilities. Fona herzogi from Utah demonstrated that some dinosaur species evolved burrowing behaviors and associated anatomical features, including powerful forelimb muscles and reinforced skeletal structures that allowed them to survive in underground environments. Preserved soft tissue revealed metabolic adaptations that were previously unknown in dinosaur biology. Chemical analysis of fossilized muscle tissue showed that some species possess the ability to switch between different metabolic pathways depending on environmental conditions. This metabolic flexibility allowed survival during periods when traditional food sources were unavailable or when environmental conditions required different energy expenditure patterns. Some species showed evidence of enhanced immune systems that allowed dinosaurs to survive in environments with high levels of toxins or pathogens. The fossil discoveries demonstrated that dinosaur evolution was far more dynamic and responsive than previously believed. Rather than following predictable evolutionary trajectories, dinosaur species showed remarkable plasticity in their ability to develop new anatomical features, behavioral strategies, and physiological capabilities when environmental conditions demanded change. These discoveries revealed that the most remarkable aspect of dinosaur survival was not their physical adaptations alone, but the sophisticated mental capabilities that guided their responses to environmental challenges. The hidden world of dinosaur intelligence. Brain reconstruction techniques developed in 2025 have revealed that dinosaurs possessed mental abilities that match or exceed those found in modern intelligent animals. The traditional image of dinosaurs as simple reptilian beasts driven purely by instinct has been completely overturned by neurological evidence that shows complex reasoning, problem-solving abilities, and sophisticated social behaviors that required advanced mental processing. High-resolution computed tomography scans have allowed scientists to examine the internal structure of dinosaur skulls with unprecedented detail. These scans reveal neural pathways that were previously invisible to researchers, showing brain organization patterns that indicate advanced cognitive functions. The cerebral cortex regions responsible for complex thinking show development levels that rival those found in modern mammals and birds. Areas associated with memory formation, spatial reasoning, and sensory integration display architectural complexity that suggests dinosaurs were capable of learning, planning, and adapting their behavior based on experience. The reconstruction process involves scanning fossilized skulls at resolutions measured in micrometers, creating three-dimensional models that show how brain tissue was organized within the cranial cavity. These models reveal that large theropod dinosaurs had brain structures similar to those found in modern corvids, which are among the most intelligent birds alive today. The hippocampus regions responsible for memory storage show extensive development, while areas associated with social cognition display complex folding patterns that indicate sophisticated information processing capabilities. Evidence of problem-solving behaviors has been preserved in fossil trackways that show dinosaurs responding to environmental challenges in ways that require planning and abstract thinking. These trackways reveal instances where dinosaurs changed their movement patterns to navigate obstacles, avoided dangerous terrain, and coordinated group movements across difficult landscapes. Some trackways show evidence of dinosaurs testing different routes before selecting optimal paths, indicating they could evaluate multiple options and choose the most effective strategy. One particularly revealing trackway site in Colorado shows evidence of a group of theropod dinosaurs that encountered a river crossing during a seasonal migration. The trackways indicate that the group spent considerable time evaluating different crossing points before selecting a location that provided the safest passage. Individual dinosaurs can be seen testing the water depth and current strength before committing to crossing, behavior that requires the ability to assess risk and make informed decisions based on environmental conditions. Isotope analysis of fossilized brain tissue has provided direct evidence of advanced sensory processing capabilities that surpass those found in modern reptiles. Chemical signatures preserved in neural tissue show that dinosaurs possessed enhanced visual processing systems capable of detecting subtle environmental changes. The isotope ratios indicate that brain regions responsible for processing sensory information were highly active and consumed significant amounts of metabolic energy, suggesting that dinosaurs relied heavily on sophisticated sensory analysis for survival. The sensory processing evidence extends beyond basic perception to include complex integration of multiple sensory inputs. Brain tissue analysis shows that dinosaurs could process visual, auditory, and chemical information simultaneously to create detailed environmental maps. This multi-sensory processing capability would have allowed them to detect approaching predators, locate food sources, and navigate complex terrain with remarkable precision. Environmental manipulation represents one of the most surprising aspects of dinosaur intelligence revealed through recent fossil discoveries. Evidence suggests that certain dinosaur species modified their surroundings to create more favorable living conditions, behavior that requires understanding of its cause and affect relationships and long-term planning. Fossil sites show evidence of dinosaurs that deliberately altered water flow patterns to create drinking pools, modified vegetation growth to improve food availability, and constructed windbreaks to protect nesting areas from harsh weather conditions. Social fossil formations provide compelling evidence of sophisticated communication systems among dinosaur populations. These formations show evidence of coordinated group activities that required complex information exchange between individuals. Fossilized gathering sites reveal patterns that indicate dinosaurs could communicate about food sources, environmental dangers, and migration routes using signals that were understood by other group members. The spatial arrangements of these social sites suggest that dinosaurs had established protocols for group decision-making and conflict resolution. The discovery of dinosaur educational sites has revolutionized our understanding of knowledge transfer between generations. These locations show evidence of adult dinosaurs teaching survival techniques to younger individuals through demonstration and practice. Fossil evidence indicates that young dinosaurs learned hunting strategies, predator avoidance techniques, and environmental navigation skills through structured interactions with experienced adults. The teaching sites show repeated use over extended periods, suggesting that dinosaur education was systematic and comprehensive. Nesting site analysis reveals parental care strategies that demonstrate remarkable behavioral sophistication. These sites show evidence of dinosaurs that modified nest construction based on environmental conditions, adjusted incubation behaviors to optimize egg development, and coordinated care duties among multiple adults. Some nesting sites show evidence of dinosaurs that created elaborate protection systems around their eggs, including camouflage structures and defensive barriers that required advanced planning and construction abilities. Evidence of environmental modification extends to landscape-scale engineering projects that benefited entire dinosaur communities. Some sites show evidence of dinosaurs that created water retention systems during drought periods, maintained travel corridors through dense vegetation, and established communal feeding areas that were used by multiple species. These projects required coordination between different dinosaur groups and long-term maintenance efforts that spanned multiple generations. Brain tissue analysis from the final period of dinosaur existence shows evidence of enhanced neural development in response to environmental stress. Dinosaurs facing extinction pressures developed increased brain complexity in areas associated with problem-solving and adaptive behavior. This neurological evidence suggests that the extinction crisis drove rapid evolution of cognitive abilities as dinosaurs struggled to survive in increasingly challenging environments. The intelligence that emerged during this period became the foundation for survival strategies that would push the boundaries of biological possibility. These cognitive advances enabled dinosaurs to develop survival capabilities that bordered on the impossible. Recent fossil discoveries reveal adaptations that emerged during Earth's most challenging periods and represent some of the most remarkable evolutionary innovations ever documented. The evidence shows that dinosaurs developed biological mechanisms that allowed them to survive environmental conditions that would have been instantly lethal to most other life forms. These survival strategies were not simple behavioral changes, but fundamental alterations to their basic biological processes that required genetic modifications occurring over thousands of years. Metabolic shutdown capabilities represent one of the most extraordinary adaptations discovered in recent fossil analysis. Bone chemistry examination reveals that some dinosaur species could dramatically reduce their metabolic rate during periods of extreme resource scarcity. This process involved shutting down non-essential organ systems while maintaining basic life functions at minimal energy levels. The isotope signatures in fossilized tissue show evidence of dinosaurs that survived extended periods with virtually no food intake by entering states of metabolic suspension similar to but far more extreme than hibernation in modern animals. The metabolic shutdown process required precise control over cellular energy production and waste elimination. Fossilized liver tissue shows evidence of modified enzyme systems that could process stored body fat with remarkable efficiency during dormancy periods. Heart muscle tissue displays adaptations that allowed cardiovascular function to continue at extremely low rates while maintaining adequate circulation to vital organs. Brain tissue analysis reveals that dinosaurs could reduce neural activity to minimal levels while preserving essential functions like breathing and temperature regulation. Environmental extremes that would have killed most life forms became survivable for certain dinosaur species through remarkable physiological adaptations. Fossil evidence from sites in Antarctica shows dinosaurs that survived in sub-zero temperatures for extended periods by developing antifreeze proteins in their blood and tissue fluids. These proteins prevented ice crystal formation in cells and maintained cellular function at temperatures that would have destroyed normal biological processes. Bone structure analysis reveals modifications that allowed continued growth and repair, even under extreme cold conditions. Desert environments posed different challenges that were overcome through equally impressive adaptations. Fossilized kidney tissue from dinosaurs found in ancient arid regions shows modifications that allowed them to concentrate urine to extraordinary levels and recycle water with near-perfect efficiency. These adaptations enabled survival on minimal water intake for periods extending beyond what any modern vertebrate could achieve. Nasal cavity modifications show evidence of enhanced water recovery from exhaled air and specialized salt glands that maintained proper electrolyte balance under extreme dehydration conditions. Dietary flexibility became crucial for survival as traditional food sources disappeared during environmental crises. Stomach content analysis reveals that some dinosaur species developed the ability to switch between completely different food sources within days or weeks. Herbivorous dinosaurs began processing animal protein when plant matter became scarce, while carnivorous species adapted to digest plant material when prey animals disappeared. This dietary switching required rapid modifications to digestive enzyme production and gut bacteria populations that would normally take generations to accomplish. The ability to process previously inedible plant matter represents one of the most remarkable digestive adaptations documented in the fossil record. Chemical analysis of fossilized stomach contents shows dinosaurs consuming plants with high levels of toxic compounds that would have been fatal to their ancestors. These dinosaurs developed enhanced liver detoxification systems and modified gut bacteria that could neutralize plant toxins and extract nutrients from fibrous material that was previously indigestible. Some species developed specialized stomach chambers that allowed fermentation of tough plant matter similar to ruminant digestion in modern mammals. Hibernation-like states extended far beyond simple seasonal dormancy to include extended periods of suspended animation lasting months or even years. Fossil evidence shows dinosaurs that entered these states during environmental crises and emerged when conditions improved. Bone growth patterns indicate that some dinosaurs suspended their normal growth cycles for extended periods and resumed development when adequate resources became available. This adaptation required precise hormonal control, systems that could maintain basic life functions while minimizing energy expenditure. Enhanced immune systems emerged as environmental toxins increased during extinction periods. Fossil evidence shows dinosaurs that survived exposure to volcanic gases, acid rain, and other environmental poisons that killed most other life forms. These immune adaptations included enhanced white blood cell production, modified liver detoxification pathways, and specialized proteins that could neutralize toxic compounds before they reached vital organs. Some species developed the ability to actively seek out and consume mineral deposits that provided protective compounds against environmental toxins. Temperature regulation capabilities allowed survival in environments with extreme temperature fluctuations. Fossilized blood vessels show modifications that permitted precise control over heat distribution throughout the body. Some dinosaurs developed the ability to raise their core temperature during cold periods while allowing extremities to cool without tissue damage. Others could lower their body temperature during heat waves while maintaining normal organ function. These adaptations required sophisticated cardiovascular modifications and specialized proteins that protected cellular structures during temperature extremes. The integration of these survival strategies created dinosaur populations that could survive through multiple extinction waves that eliminated less adaptable species. Each wave of environmental crisis eliminated dinosaurs that lacked specific adaptations while allowing those with appropriate survival mechanisms to persist. The survivors from each wave became increasingly specialized for crisis survival, developing ever more extreme adaptations that pushed the boundaries of biological possibility. These extraordinary survival capabilities explain how dinosaur populations persisted through environmental conditions that should have caused immediate extinction, but the true scope of their challenge was far more complex than anyone had imagined. The multiple extinction waves revealed. Advanced climate modeling completed in 2025 has reconstructed a series of environmental catastrophes that created waves of destruction across different time periods and geographic regions. This discovery explains why the fossil record shows such complex patterns of dinosaur disappearance and why some species survived far longer than others. The extinction process was not a single catastrophic event, but rather a prolonged series of environmental crises that tested the limits of dinosaur adaptability over extended periods. Climate modeling conducted using supercomputer systems has revealed the intricate timing of these extinction waves. The simulations show that environmental stress began building approximately 68 million years ago with the onset of massive volcanic eruptions in what is now the Indian subcontinent. These eruptions released enormous quantities of sulfur dioxide and other toxic gases into the atmosphere, creating the first wave of environmental stress that affected dinosaur populations across Asia and parts of Europe. The modeling data indicates that this initial crisis lasted approximately 200,000 years and eliminated roughly 30% of existing dinosaur species. Regional variations in extinction timing become apparent when examining fossil evidence from different continents. North American dinosaur populations experienced their first major crisis around 67.5 million years ago when atmospheric changes altered precipitation patterns and temperature distributions. European populations faced different challenges as ocean chemistry modifications affected coastal ecosystems where many dinosaur species fed and bred. African dinosaur communities encountered their initial extinction pressures later due to geographic isolation that temporarily protected them from global atmospheric changes. Volcanic activity created cascading environmental effects that generated multiple waves of extinction pressure. The massive eruptions in India released an estimated 1.5 million cubic kilometers of lava over a period of 30,000 years, fundamentally altering global atmospheric composition. These eruptions occurred in distinct phases separated by periods of relative calm, creating environmental stress waves that affected dinosaur populations at different times. Each volcanic phase released different combinations of gases and particulates that created unique environmental challenges requiring different survival adaptations. Ocean chemistry changes triggered ecological collapses that spread from marine environments to terrestrial ecosystems. The first wave of ocean acidification occurred approximately 67 million years ago when increased atmospheric carbon dioxide dissolved into seawater, reducing pH levels by an estimated 0.4 units. This acidification eliminated many marine organisms that formed the base of ocean food chains, creating ripple effects that reached coastal dinosaur populations dependent on marine resources. Secondary ocean chemistry changes occurred when volcanic ash altered nutrient distributions and created toxic algal blooms that poisoned water sources used by terrestrial dinosaurs. Climate oscillations created repeated challenges that tested dinosaur survival capabilities over extended periods. Temperature fluctuations of up to 8 degrees Celsius occurred over periods of thousands of years, forcing dinosaur populations to adapt to rapidly changing thermal environments. These oscillations were not gradual changes, but rather rapid shifts that occurred within decades, creating selective pressures that favored dinosaurs with flexible physiological systems. Evidence of recovery periods between extinction waves provides crucial insights into dinosaur resilience and adaptability. Fossil sites in Montana and Alberta show clear evidence of dinosaur population rebounds during environmental recovery periods that lasted 10,000 to 50,000 years. These recovery phases allowed surviving populations to expand their ranges and diversify into ecological niches left vacant by extinct species. Population genetic analysis suggests that some dinosaur lineages actually increased in diversity during these recovery periods as they evolved to exploit new environmental opportunities. The wave pattern of extinctions eliminated different types of species based on their specific biological adaptations and ecological requirements. The first wave primarily affected large, herbivorous dinosaurs with specialized digestive systems that could not adapt to changing plant communities. Carnivorous dinosaurs faced extinction during the second wave when their prey species disappeared and they could not transition to alternative food sources. Smaller, omnivorous species survived longer by switching between different dietary strategies as environmental conditions changed. Each extinction wave created increasingly specialized survival requirements that eliminated species lacking specific adaptations. The third wave, approximately 66.5 million years ago, eliminated dinosaurs that could not survive in low-oxygen environments created by atmospheric changes. The fourth wave removed species that lacked enhanced detoxification systems needed to process environmental toxins. Surviving populations became increasingly specialized for crisis survival, developing ever more extreme adaptations that allowed persistence through multiple environmental challenges. Recovery periods between waves show evidence of rapid evolutionary changes in surviving dinosaur populations. Bone structure analysis reveals that some species modified their skeletal systems within thousands of years to adapt to changing environmental conditions. Dental modifications occurred even more rapidly as dinosaurs adapted to new food sources that became available during recovery periods. These rapid evolutionary changes demonstrate that dinosaurs possessed remarkable genetic flexibility that allowed quick adaptation to environmental opportunities. The complexity of the wave pattern explains why different dinosaur lineages show such varied extinction timelines in the fossil record. Flying dinosaurs experienced different extinction pressures than ground-dwelling species because they could migrate to avoid regional environmental problems. Aquatic dinosaurs faced unique challenges related to water chemistry changes that occurred independently of terrestrial environmental issues. The final extinction wave coincided with the asteroid impact approximately 66 million years ago, but this event occurred when dinosaur populations were already severely reduced by previous waves. The asteroid impact created environmental conditions that eliminated the remaining specialized populations that had survived previous crises. The impact generated atmospheric dust that blocked sunlight for extended periods, creating conditions that were impossible for any remaining dinosaur species to survive regardless of their previous adaptations. This wave pattern of extinction provides a new framework for understanding mass extinction events and their effects on evolutionary processes. The discovery reveals that extinction can occur through multiple waves separated by recovery periods, fundamentally changing how scientists interpret fossil evidence. However, the most remarkable aspect of dinosaur survival was not their ability to endure these waves, but their capacity to actively reshape their environments in response to crisis conditions. Advanced ecosystem engineering by dinosaurs. Evidence of dinosaur engineering projects reveals construction capabilities that transformed entire landscapes across prehistoric continents. These creatures functioned as sophisticated ecosystem engineers who actively modified their surroundings to create conditions supporting their survival and the survival of other species. Fossil evidence shows dinosaurs constructed complex infrastructure systems including water management networks, vegetation cultivation areas, and shelter systems that persisted for thousands of years. These engineering projects required long-term planning and coordinated effort between different species groups, demonstrating environmental manipulation that rivals modern human activities. Water retention systems built by dinosaurs represent some of the most impressive engineering achievements documented in the fossil record. Geological surveys of ancient riverbeds show evidence of deliberate channel modifications that created seasonal water storage areas during dry periods. These systems involved constructing earthen barriers using compacted soil and organic matter that could hold water for extended periods. The engineering work required coordinated effort from multiple dinosaur species working together to move enormous quantities of earth and construct durable barrier systems that could withstand seasonal flooding. Excavation sites in Colorado and Utah revealed dinosaur-constructed water collection systems that channeled rainfall into underground storage areas. These systems included surface channels that directed water flow into natural depressions that were then modified to increase storage capacity. Construction work involved removing loose sediment and lining storage areas with compacted clay that prevented water loss through seepage. Some sites show evidence of maintenance work performed over decades, indicating that dinosaurs returned regularly to repair and upgrade their water management systems. Plant cultivation by dinosaurs extended far beyond simple foraging to include active management of vegetation communities that provided optimal nutrition and habitat conditions. Fossil evidence shows areas where dinosaurs selectively removed competing plant species to promote growth of preferred food plants. These cultivation sites reveal patterns of soil preparation that included removal of rocks and debris, addition of organic matter from dinosaur waste, and creation of optimal growing conditions for specific plant species. The cultivation work required understanding of plant growth requirements and seasonal timing that demonstrates sophisticated agricultural knowledge. Sites in Montana show evidence of dinosaur-managed grasslands where preferred grass species were promoted through selective grazing patterns that eliminated competing vegetation. These managed areas show increased soil fertility from concentrated dinosaur waste and evidence of fire management that prevented invasion by woody plants. Grassland management required coordination between different dinosaur species with complementary grazing behaviors that maintained optimal plant community composition over extended periods. Some managed grasslands show evidence of continuous use for thousands of years with ongoing maintenance work. Underground shelter networks constructed by dinosaurs provided protection from extreme weather conditions and predators during vulnerable periods. These shelter systems included excavated chambers connected by tunnel networks that could accommodate multiple individuals or family groups. Construction work involved removing enormous quantities of soil and rock to create chambers large enough for adult dinosaurs while maintaining structural integrity that prevented collapse. Some shelter networks extend for hundreds of meters underground and include multiple entrance points and ventilation systems. Fire management by dinosaurs represents one of the most sophisticated aspects of their ecosystem engineering capabilities. Evidence shows that certain dinosaur species use controlled burning to promote growth of preferred plant species and prevent accumulation of dead vegetation that could fuel dangerous wildfires. Charcoal deposits associated with dinosaur activity sites show patterns of regular burning that maintained optimal vegetation composition and prevented large-scale fires that could destroy entire ecosystems. Fire management work required understanding of weather patterns and vegetation growth cycles that allowed precise timing of burning activities. Burn sites show evidence of careful preparation that included creation of fire breaks and removal of flammable materials from areas requiring protection. Some sites reveal evidence of dinosaurs that started fires using friction methods and controlled their spread through construction of earthen barriers and water diversions. Controlled burning promoted growth of nutritious grasses and prevented establishment of dense forests that would have been unsuitable for many dinosaur species. Fire management sites show evidence of use over thousands of years with regular maintenance of fire breaks and burning schedules. Symbiotic relationships between dinosaurs and other organisms created complex ecological networks that enhanced survival for all participating species. Evidence shows that some dinosaur species developed partnerships with plant species that provided mutual benefits through specialized pollination services and seed dispersal activities. These relationships involved dinosaurs that modified their feeding behaviors to promote plant reproduction while receiving enhanced nutrition from specialized plant tissues. The symbiotic relationships required behavioral modifications that developed over thousands of years and created stable ecological partnerships. Interspecies cooperation in ecosystem management involved coordination between different dinosaur species with complementary engineering capabilities. Large herbivorous dinosaurs provided earth-moving capabilities for major construction projects, while smaller species contributed precision work and maintenance activities. Carnivorous dinosaurs participated by controlling populations of animals that could damage engineered systems and by providing organic matter for soil improvement. The cooperation required communication systems and coordinated planning that allowed multiple species to work together on complex engineering projects. These engineering abilities represent a form of proto-agriculture that involved active management of plant and animal communities to create optimal conditions for survival and reproduction. Agricultural practices included soil preparation, selective breeding of preferred plant varieties, and integrated pest management that maintained ecological balance. Dinosaurs developed crop rotation systems that maintained soil fertility and prevented depletion of nutrients from continuous cultivation. Agricultural systems included storage facilities for surplus plant material and water management systems that supported cultivation during dry periods. The engineering projects helped entire ecosystems survive crisis periods by creating stable resource bases and protected habitats that buffered against environmental changes. Water retention systems provided reliable water sources during drought periods, while plant cultivation areas maintained food supplies when natural vegetation became scarce. Shelter networks protected vulnerable species during extreme weather events, and fire management prevented catastrophic burns that could have destroyed entire ecosystems. These sophisticated engineering capabilities created resilient ecological networks that should have protected dinosaur populations from environmental catastrophes. Yet even these remarkable adaptations would prove insufficient against the complex series of disasters that began with a single cosmic impact. The cosmic collision that struck Earth 66 million years ago initiated a sequence of environmental disasters that would unfold over thousands of years. Advanced computer modeling completed in 2025 has reconstructed the asteroid impact with unprecedented precision, revealing effects that were far more complex than previous estimates suggested. The simulations show that the 10-kilometer-wide asteroid that struck the Yucatan Peninsula released energy equivalent to billions of nuclear weapons, but this was only the beginning of the environmental chaos that followed. The impact injected an estimated 400 million tons of dust, soot, and sulfur compounds into the upper atmosphere, creating a global blanket that blocked sunlight for extended periods. These climate-active aerosols remained suspended in the atmosphere for over 4 years, creating what researchers term a global impact winter that fundamentally altered Earth's climate system. The impact destabilized geological processes that had remained stable for millions of years, triggering a chain reaction of environmental disasters that spread across the planet. The initial shock wave from the collision caused massive earthquakes that extended far beyond the impact site, fracturing rock formations and destabilizing underground magma chambers. These geological disturbances created pathways for volcanic activity that would continue for millennia after the initial impact. Massive volcanic eruptions triggered by the impact released enormous quantities of greenhouse gases that created a complex and unstable climate system. The volcanic activity began within decades of the impact and continued for thousands of years, pumping carbon dioxide, methane, and other climate-altering gases into the atmosphere. These emissions created a greenhouse effect that followed the initial cooling period, subjecting the planet to extreme temperature fluctuations that made environmental adaptation nearly impossible. The volcanic emissions also released toxic gases, including sulfur dioxide and hydrogen sulfide that poisoned air and water sources across vast regions. Ocean current systems that had circulated for millions of years were fundamentally altered by the impact, creating new patterns of water circulation that affected global climate regulation. The impact altered ocean chemistry through the injection of impact debris and the disruption of seafloor sediments that had accumulated over geological time periods. These changes affected marine ecosystems that formed the base of global food chains, creating cascading effects that reached terrestrial environments. The altered ocean currents changed heat distribution patterns that had maintained stable regional climates, creating new zones of extreme temperature and precipitation that challenged existing life forms. Atmospheric circulation patterns underwent dramatic changes that created regional climate zones unlike anything that had existed during the previous 100 million years. The impact debris in the upper atmosphere disrupted normal wind patterns and created new systems of air circulation that distributed heat and moisture in unprecedented ways. These atmospheric changes created regions of extreme drought alongside areas of excessive precipitation, forcing organisms to adapt to environmental conditions that fluctuated rapidly over short time periods. The disrupted atmospheric circulation also affected seasonal patterns that many species depended on for reproduction and migration cycles. The cascade of environmental instabilities created by the impact generated conditions that were far more challenging than the initial collision itself. Global temperatures dropped by as much as 7.2 degrees Fahrenheit during the impact winter, while rainfall decreased by approximately 15% due to reduced evaporation from the cooled surface. The ozone layer depleted by up to 32%, allowing dangerous levels of ultraviolet radiation to reach Earth's surface. These combined effects created an environment that was hostile to most existing life forms and required unprecedented adaptations for survival. Evidence from fossil sites reveals that some dinosaur populations actually survived the initial impact and its immediate aftermath, contradicting the traditional view of instant extinction. Bone chemistry analysis shows that certain dinosaur species continued to exist for decades or even centuries after the impact, indicating that the extinction process was far more gradual than previously believed. These surviving populations faced increasingly difficult environmental conditions as the cascade of post-impact effects intensified over time. The survivors show evidence of rapid evolutionary changes as they adapted to the deteriorating environmental conditions. Regional variations in post-impact conditions created dramatically different survival scenarios across the planet. Areas near the impact site experienced immediate devastation, while regions on the opposite side of the planet faced different challenges related to atmospheric disruption and climate change. Some geographic areas provided temporary refuges where environmental conditions remained relatively stable, allowing dinosaur populations to persist longer than in other regions. Tropical regions faced intense heat and atmospheric toxicity from volcanic gases, while polar areas dealt with extended periods of darkness and extreme cold that exceeded anything in their previous history. Mountain regions provided some protection from atmospheric changes but faced challenges related to altered precipitation patterns and temperature extremes. Coastal areas experienced massive tsunamis and long-term changes in sea level that eliminated established ecosystems and forced surviving species to adapt to entirely new environmental conditions. The complexity of post-impact environmental conditions explains why the extinction process took thousands of years to complete rather than occurring within a single generation. Different species faced elimination at different times based on their specific environmental requirements and adaptive capabilities. The gradual nature of the extinction process allowed some species to develop remarkable survival adaptations before ultimately succumbing to environmental pressures that exceeded their adaptive limits. Understanding the complexity of the post-impact extinction process fundamentally changes our view of mass extinctions and their effects on evolutionary processes. The discovery that major extinction events can unfold over extended periods through cascading environmental effects provides new insights into how life responds to catastrophic environmental changes. As environmental conditions deteriorated across different regions at different rates, Surviving dinosaur populations faced an unprecedented challenge that would test their most sophisticated survival capabilities. The response to this crisis would reveal movement patterns and navigation abilities that had remained hidden throughout their evolutionary history. Dinosaur migration mysteries solved. Chemical analysis of fossilized teeth revealed that dinosaurs traveled across entire continents during their migrations, fundamentally changing our understanding of their survival capabilities and geographic distribution. These massive journeys covered distances that exceeded modern animal migrations by thousands of miles, demonstrating navigational abilities and physical endurance that surpassed anything previously documented in the fossil record. The discovery of these continental-scale migration routes emerged from isotope analysis of dinosaur teeth and bones collected from sites separated by vast distances, revealing chemical signatures that could only result from animals that consumed food and water from multiple geographic regions during their lifetimes. Isotope analysis techniques developed in 2025 allowed researchers to trace seasonal movement patterns with unprecedented precision by examining the chemical composition of dinosaur tissue. These analyses reveal that certain dinosaur species moved between regions with distinctly different geological and climatic characteristics, following predictable patterns that corresponded to seasonal changes in resource availability. The isotope signatures show that some dinosaurs traveled from tropical coastal regions to temperate mountain areas and back again within single years, covering distances that would have required months of continuous travel at sustainable speeds. Fossilized teeth provided the most detailed evidence of these migration patterns by recording the isotopic composition of water and vegetation consumed in different locations. Teeth from individual dinosaurs show layered isotope signatures that correspond to different geographic regions, creating a chronological record of their travels. Some specimens show evidence of annual migration cycles that persisted for decades, indicating that these journeys were not random wandering, but established routes that were repeated year after year with remarkable consistency. Mass migrations involving multiple species created coordinated movements that enhanced survival opportunities for entire dinosaur communities. Fossil trackway sites reveal evidence of different dinosaur species traveling together along established routes, suggesting that these migrations involved complex social coordination between groups that would normally compete for resources. The trackways show evidence of temporary alliances between herbivorous and carnivorous species that provided mutual benefits during long-distance travel, with herbivores providing early warning of environmental dangers while carnivores offered protection from predators. The coordination of these multi-species migrations required sophisticated communication systems that allowed different dinosaur groups to synchronize their movements and share information about route conditions. Fossil evidence suggests that certain species served as migration leaders that possessed superior navigational abilities and guided mixed species groups along optimal routes. The social dynamics of these migrations involved temporary hierarchies that formed during travel periods and dissolved when groups reached their destinations and resumed normal territorial behaviors. Environmental cues used by dinosaurs for navigation included magnetic field detection, celestial navigation, and chemical trail following that allowed precise route finding across vast distances. Fossilized inner ear structures show modifications that would have allowed detection of Earth's magnetic field, providing a biological compass system that functioned regardless of weather conditions or time of day. Enlarged brain regions associated with spatial memory and navigation suggest that dinosaurs could create detailed mental maps of migration routes and remember landmarks and environmental features across thousands of miles of territory. Chemical trail following capabilities allowed dinosaurs to follow scent markers left by previous migrations, creating established pathways that became more distinct with repeated use. Fossilized nasal cavity structures show enhanced olfactory systems that could detect chemical signatures from enormous distances, allowing dinosaurs to locate migration routes even when visual landmarks were obscured by weather or vegetation. These chemical navigation systems worked in conjunction with other navigational methods to provide redundant guidance systems that ensured successful completion of long-distance journeys. Migration corridors, used continuously for millions of years, created permanent pathways that shaped landscape evolution and ecosystem development across entire continents. These corridors follow geographic features that provided optimal travel conditions, including river valleys, mountain passes, and coastal plains that offered reliable water sources and suitable terrain for large dinosaur groups. The repeated use of these corridors created worn pathways that can still be detected in geological formations, showing evidence of continuous traffic that persisted across multiple geological periods. Regional environmental crises that would have eliminated local dinosaur populations became survivable through migration to areas with more favorable conditions. Drought periods that devastated local ecosystems could be survived by relocating to regions with adequate water and vegetation, while volcanic activity that poisoned local environments could be avoided by moving to unaffected areas. The ability to relocate entire populations during environmental crises provided a survival strategy that allowed dinosaur species to persist through regional disasters that would have caused local extinctions. The timing of these survival migrations became increasingly precise as environmental monitoring capabilities improved through evolutionary adaptation. Evidence suggests that dinosaurs developed the ability to detect environmental changes from increasing distances, allowing migration initiation before local conditions became lethal. This early warning system involved enhanced sensory capabilities that could detect subtle changes in atmospheric chemistry, electromagnetic patterns, and vegetation health that indicated approaching environmental problems. Environmental change detection capabilities extended beyond immediate sensory range to include monitoring of distant conditions through atmospheric and chemical signals. Some dinosaur species developed the ability to detect volcanic activity from hundreds of miles away by sensing changes in atmospheric chemistry and electromagnetic fields. Others could detect approaching weather patterns days or weeks in advance by monitoring atmospheric pressure changes and chemical signatures carried by wind currents from distant regions. Migration timing became critical during extinction periods when environmental conditions changed rapidly and unpredictably across large geographic areas. The ability to initiate migrations at optimal times determined whether dinosaur populations could successfully relocate to safe areas before local conditions became unsurvivable. Species that developed superior environmental monitoring capabilities could begin migrations early enough to avoid the worst effects of environmental crises, while those with less sensitive detection systems often began migrations too late to escape deteriorating conditions. These migration abilities extended dinosaur survival far beyond expected timelines by providing access to refuge areas that remained habitable during regional extinction events. The combination of long-distance travel capabilities and environmental monitoring systems allowed dinosaur populations to persist in isolated areas where local conditions remained favorable while surrounding regions experienced environmental collapse. However, as environmental pressures intensified across the globe, even the most remote locations would eventually be discovered by desperate populations seeking their final sanctuary: the last dinosaur populations. Remote refugia scattered across the globe became the final battlegrounds where dinosaur populations made their desperate last stand against extinction. These isolated pockets of survival functioned as biological arcs where dinosaur life persisted for thousands of years after the main extinction event eliminated populations across most of the planet. The locations of these final strongholds reveal incredible determination and adaptation as dinosaurs retreated to the most extreme and inhospitable environments on Earth in their struggle to survive. Isolated populations that survived in extreme environments developed characteristics that would have been unimaginable in their ancestors. These populations faced environmental conditions that pushed the boundaries of biological survival, forcing rapid evolutionary changes that occurred within centuries rather than millennia. The fossil evidence from these Refugia sites shows dinosaur remains with bone structures and chemical signatures that indicate survival in environments with extreme temperatures, toxic atmospheric conditions, and severely limited food resources. Fossils from Refugia sites show evidence of rapid evolutionary changes that occurred as isolated populations adapted to their harsh environments. Bone growth patterns indicate that these dinosaurs modified their metabolic processes to function efficiently under extreme stress conditions. Skeletal modifications show adaptations for survival in environments with limited oxygen, extreme temperatures, and toxic atmospheric conditions. The speed of these evolutionary changes suggests that extinction pressure drove genetic modifications that would normally require thousands of generations to develop. The survival adaptations developed by these final populations exceeded anything previously documented in the fossil record. Some populations developed the ability to survive in volcanic regions by processing toxic gases and extreme heat that would have been instantly lethal to normal dinosaurs. Others adapted to polar conditions by developing antifreeze proteins and specialized metabolic processes that allowed function at temperatures approaching absolute biological limits. Forest-dwelling populations developed enhanced immune systems and detoxification capabilities that allowed survival in environments poisoned by atmospheric toxins. Volcanic refugia provided protection through geothermal energy that maintained habitable temperatures during the impact winter period. These populations developed respiratory modifications that allowed them to process volcanic gases and extract oxygen from chemically altered atmospheres. Bone chemistry analysis shows that volcanic refugia dinosaurs consumed mineral-rich volcanic ash and developed specialized digestive systems that could extract nutrients from previously inedible materials. The geothermal environments provided stable temperatures that buffered against the extreme climate fluctuations that eliminated populations in other regions. Polar refugia populations survived by developing unprecedented cold weather adaptations that allowed function in sub-zero temperatures for extended periods. These populations modified their cardiovascular systems to prevent freezing damage and developed specialized fat storage systems that provided energy during extended periods of reduced activity. The polar dinosaurs developed behavioral adaptations that included group huddling and shared body heat conservation techniques that maximized survival during the darkest periods of the impact winter. Evidence shows that these populations created insulated shelters using available materials and maintained social structures that enhanced group survival. Deep forest refugia provided protection through dense vegetation that filtered atmospheric toxins and maintained local climate stability. These populations developed arboreal adaptations that allowed them to exploit vertical forest resources and avoid ground-level environmental hazards. Forest-dwelling dinosaurs modified their dietary patterns to consume tree bark, roots, and other forest materials that provided nutrition when normal food sources disappeared. The dense forest canopy created microenvironments with stable temperatures and humidity levels that buffered against the extreme climate changes affecting open areas. These refugia maintained dinosaur life for thousands of years through carefully balanced ecosystems that maximized resource utilization and minimized environmental stress. The populations developed sophisticated resource management strategies that included seasonal migration within refugia areas and coordinated breeding programs that maintained genetic diversity within small populations. Evidence shows that refugia populations established sustainable hunting and foraging patterns that prevented overexploitation of limited resources while maintaining population stability over extended periods. Hybrid species emerged from desperate survival attempts as isolated populations faced genetic bottlenecks that threatened their continued existence. These hybrid forms represent evolutionary experiments that occurred as populations adapted to extreme conditions and limited genetic diversity. Fossil evidence shows species that combined characteristics from different dinosaur lineages, creating forms that possessed enhanced survival capabilities but reduced reproductive success. The hybrid populations represent the final evolutionary attempts of dinosaur species to adapt to impossible environmental conditions. The gradual decline of refugia populations occurred as environmental pressures continued to intensify over thousands of years. Each refugia faced unique challenges that eventually overwhelmed even the most remarkable survival adaptations. Volcanic refugia populations succumbed to increasing toxicity levels that exceeded their detoxification capabilities. Polar populations faced extending periods of darkness and cold that depleted their energy reserves beyond recovery. Forest refugia populations experienced resource depletion as vegetation communities collapsed under continued environmental stress. Evidence of the very last dinosaur individuals provides a poignant picture of their final struggles against impossible odds. These specimens show signs of extreme nutritional stress and desperate attempts to survive on increasingly inadequate food sources. Bone chemistry analysis reveals that the final individuals consumed previously inedible materials and survived on minimal nutrition for extended periods before succumbing to starvation and environmental toxins. The last dinosaurs show evidence of continued social cooperation and parental care, even under the most desperate circumstances. The final Refugia populations came remarkably close to surviving the extinction event entirely. Some populations persisted for over 3,000 years after the main extinction, demonstrating that dinosaur survival was not impossible but rather dependent on access to specific environmental conditions and resources. The evidence suggests that if environmental conditions had stabilized even slightly sooner, some Refugia populations might have survived to recolonize areas where conditions improved. These final populations represent the ultimate testament to dinosaur resilience and adaptability in the face of impossible environmental challenges. Their survival for thousands of years after the main extinction demonstrates that these creatures possessed remarkable evolutionary flexibility and determination. Yet the story of which creatures ultimately survived the extinction reveals patterns that challenge everything scientists thought they knew about evolutionary success. The fossil record reveals that survival depended on specific biological traits rather than evolutionary dominance or physical strength. Small mammals, birds, crocodiles, turtles, and certain marine organisms persisted through the environmental catastrophe, while the mighty dinosaurs disappeared entirely. These survivors possessed precise combinations of characteristics that proved essential for enduring the prolonged chaos that followed the asteroid impact. Body size emerged as the most critical factor determining survival chances during the extinction crisis. Creatures weighing less than 25 kilograms had significantly higher survival rates than larger organisms because they required fewer resources and could exploit smaller food sources that remained available during environmental collapse. Small mammals survived by consuming seeds, roots, and insects that persisted in underground environments protected from surface devastation. These creatures could maintain stable populations on resource quantities that would have been insufficient to support single large dinosaurs. Metabolic efficiency separated survivors from victims through energy conservation capabilities that proved essential during resource scarcity. Creatures with lower metabolic rates required less food and could survive extended periods without regular feeding, while high metabolism dinosaurs faced starvation when food sources disappeared. Cold-blooded reptiles like crocodiles and turtles survived by reducing their activity levels and entering dormant states that minimized energy expenditure. Their metabolic flexibility allowed survival on occasional feeding that would have been impossible for warm-blooded dinosaurs with constant energy requirements. Dietary flexibility determines survival through the ability to process different food sources as environmental conditions changed. Omnivorous creatures survived by switching between plant and animal matter as availability fluctuated, while specialized feeders faced extinction when their preferred food sources disappeared. Small mammals consumed seeds, nuts, and roots that remained buried in soil during the impact winter, providing reliable nutrition when surface vegetation died. Birds survived by eating seeds and small prey that persisted in protected microenvironments, while large herbivorous dinosaurs starved when plant communities collapsed. Behavioral adaptability became more crucial than physical adaptations for surviving the rapidly changing post-impact environment. Creatures that could modify their behavior patterns, feeding strategies, and habitat preferences survived by adapting to new environmental conditions. Small mammals demonstrated remarkable behavioral plasticity by exploiting new ecological niches and adjusting their activity patterns to avoid environmental dangers. Birds modified their migration routes and nesting behaviors to cope with altered climate patterns and food availability. The ability to exploit underground environments provided crucial protection from surface environmental devastation. Burrowing mammals survived by accessing resources and maintaining stable temperatures in subterranean refuges that protected them from atmospheric toxins and temperature extremes. These underground habitats contained food sources including roots, fungi, and invertebrates that remained available when surface ecosystems collapsed. Soil environments provided insulation that maintained habitable temperatures during the impact winter when surface temperatures dropped to lethal levels. Aquatic environments offered protection that allowed certain species to survive through environmental changes that eliminated terrestrial populations. Freshwater environments maintained more stable conditions than terrestrial habitats and contained food sources that persisted through the crisis period. Crocodiles and turtles survived in aquatic refuges that provided thermal stability and access to fish, amphibians, and plant matter that remained available when terrestrial food sources disappeared. These aquatic survivors could also exploit both water and land resources as environmental conditions changed. Some species survived by completely transforming their ecological roles and exploiting opportunities created by the extinction of dominant species. Small mammals expanded into ecological niches previously occupied by dinosaurs, developing new feeding strategies and habitat preferences that allowed exploitation of available resources. These ecological role changes occurred rapidly as survivors adapted to fill vacant niches in post-extinction ecosystems. The transformation process involved behavioral modifications that allowed exploitation of new food sources and habitat types. Reproductive strategies played crucial roles in determining which species persisted through the extinction crisis. Species with rapid reproductive cycles could replace population losses more quickly than those with slower breeding rates. Small mammals with short generation times could adapt genetically to changing environmental conditions through natural selection, operating over dozens of generations during the crisis period. Species with extended parental care and complex social structures faced greater challenges maintaining population stability under extreme environmental stress. The geographic distribution of survival showed that certain regions provided better refugia than others for different types of organisms. High-latitude regions offered some protection from the worst effects of atmospheric disruption, while tropical areas provided thermal stability that benefited cold-blooded survivors. Coastal regions offered access to both terrestrial and marine resources that enhanced survival opportunities. The variation in regional survival rates demonstrates that extinction was not uniformly distributed, but rather created complex patterns of survival and death across different environments. These survival patterns inform our understanding of current extinction risks by revealing which biological traits provide resilience against environmental catastrophe. Species with small body sizes, flexible diets, and rapid reproductive rates show greater resistance to environmental change than large specialists with complex ecological requirements. The ability to exploit multiple habitat types and modify behavior patterns provides crucial advantages during periods of environmental instability. The lessons from prehistoric survival patterns apply directly to modern conservation strategies facing climate change and habitat destruction. Protecting small populations of adaptable species may be more effective than focusing solely on large charismatic species that require extensive resources. Maintaining habitat diversity and connectivity allows species to exploit multiple ecological niches and adapt to changing environmental conditions. Understanding which traits promote survival during environmental crises can guide conservation priorities and help predict which modern species are most likely to persist through current environmental challenges. These discoveries reveal that extinction events are not random cosmic accidents, but complex processes governed by specific biological principles. The patterns of survival and death during the dinosaur extinction demonstrate that evolutionary success depends on adaptability rather than dominance, flexibility rather than specialization. The research reveals that dinosaur extinction was not about evolutionary limits, but about scientific measurement errors that masked their true stability. Advanced occupancy modeling completed in 2025 demonstrates that a parent dinosaur declined before the asteroid impact resulted from sampling biases rather than actual population decreases. Fossil collection patterns created artificial scarcity that suggested dinosaurs were already failing when they were actually maintaining stable populations across diverse environments. These discoveries fundamentally change how we understand mass extinction events and their underlying causes. The complexity of dinosaur survival strategies shows that traditional extinction models failed to account for sampling limitations that distorted our understanding of prehistoric population dynamics. New modeling approaches reveal we must reconsider mass extinction drivers and sampling biases to accurately interpret